x plus 2 times x plus 3 times x plus 4 times x plus 5 equals 48. Now, the absolute key to solving this kind of problem is recognizing the pattern and using a substitution. You do not want to multiply all 4 of those terms together right away. That would give you a massive 4th-degree polynomial, and factoring that beast would be a nightmare. So, the first and most crucial step is rearranging and grouping. The goal is to pair up the binomials so that when you multiply them, they give you the same first 2 terms. How do we do that? We look at the constants. We have 2, 3, 4, and 5. We need to pair them up so the sum of the constants is the same in both pairs. If you pair 2 with 3, the sum is 5. If you pair 4 with 5, the sum is 9. No good. But if you pair the first and the last, 2 and 5, you get a sum of 7. And if you pair the 2 inner ones, 3 and 4, you also get a sum of 7. This is the magic key. So, we rewrite the equation, grouping the terms. We have the group of x plus 2 and x plus 5, and the other group is x plus 3 and x plus 4. The entire product still equals 48. Now, let's move to expansion and simplification. We're going to expand each of those 2 groups. Starting with the first group, x plus 2 times x plus 5, using the FOIL method, we get x squared plus 5x plus 2x plus 10. Combining those middle x terms gives us x squared plus 7x plus 10. See that 7x? That's where the grouping paid off. Now let's expand the second group, x plus 3 times x plus 4. FOIL gives us x squared plus 4x plus 3x plus 12. Combining the x terms here gives us x squared plus 7x plus 12. So now the whole equation looks much cleaner. We have x squared plus 7x plus 10 times x squared plus 7x plus 12 equals 48.
Look closely at that new equation. Do you see the identical part? It's the x squared plus 7x in both factors. This is where we bring in our substitution. This is the step that turns a scary 4th-degree equation into a super manageable 2nd-degree or quadratic equation. Let's make a simple substitution. The original solution in the image chose to let the entire first factor, x squared plus 7x plus 10, equal a new variable, p. So, we write, let p equal x squared plus 7x plus 10. Now the first factor is just p. What about this second factor, x squared plus 7x plus 12? Well, that's just 2 more than the first factor, right? It's x squared plus 7x plus 10 plus 2. So, this second factor is simply p plus 2. Substituting these into our equation, we get p times p plus 2 equals 48. This is beautiful. We've transformed a complex polynomial problem into a simple quadratic equation in p. Let's solve it. First, we expand the left side. P squared plus 2p. This equals 48. To solve a quadratic, we always want to set it equal to 0, so we subtract 48 from both sides. We get p squared plus 2p minus 48 equals 0. Now we factor this quadratic. We need 2 numbers that multiply to minus 48 and add up to positive 2. A little trial and error, and you'll find that those numbers are positive 8 and negative 6. So, we can factor the equation into p plus 8 times p minus 6 equals 0. This gives us our 2 possible values for p. P could equal minus 8 or p could equal 6. We are not done yet though. Remember, the original problem asked for x, not p. So the final stage is resubstitution and solving for x. we have to take each value of p and plug it back into our substitution equation. X squared plus 7x plus 10 equals p. Let's start with case 1. P equals -8. We plug it in. X squared plus 7x plus 10 equals -8. Set it to 0 by adding 8 to both sides. X squared plus 7x plus 18 equals 0. This is a new quadratic equation, and we need the quadratic formula to solve it because it won't factor nicely. The formula is x equals -b plus or minus the square root of b squared minus 4ac, all divided by 2a. In this equation, a is 1, b is 7, and c is 18. Plugging the numbers in, x equals -7 plus or minus the square root of 7 squared minus 4 times 1 times 18, all over 2 times 1. 7 squared is 49. 4 times 18 is 72. So under the square root, we have 49 minus 72, which is -23. Aha! A negative number under the square root means our solutions are complex or imaginary numbers. The square root of -23 is I times the square root of 23, where I is the imaginary unit. So the first two roots are x equals -7 plus or minus I times the square root of 23, all divided by 2. That's 2 of our 4 solutions.
Now for case 2, p equals 6. Plug it back into the substitution equation. X squared plus 7x plus 10 equals 6. Set it to 0 by subtracting 6 from both sides. X squared plus 7x plus 4 equals 0. Again, this quadratic doesn't factor, so back to the quadratic formula. Here, a is 1, b is 7, and c is 4. Plugging the numbers in, x equals -7 plus or minus the square root of 7 squareds minus 4 times 1 times 4, all over 2. 7 squared is 49. 4 times 4 is 16. So under the square root, we have 49 minus 16, which is 33. Since 33 is positive, these solutions will be real numbers. And since 33 isn't a perfect square, they'll be irrational. So the final two roots are x equals -7 plus or minus the square root of 33, all divided by 2. So, in the end, that big, intimidating polynomial equation actually had 4 solutions. 2 of them are complex numbers from the p equals -8 case, and 2 of them are real, irrational numbers from the p equals 6 case. That's how you crush a problem like this. It all comes down to that clever regrouping at the very beginning to enable the simple substitution. You got this.